Good morning. Welcome back to the Digital Technologies in an Animal-centric Dairy Industry webinar series. My name is Laura Hunter. I'm a scientist at AgResearch in animal behavior and welfare, and I've also been the project lead for the past few years on this project. So I'll be the host for our webinar series today. We've got also Jenna and Tash working in the background producing, so thanks to them. Just as a reminder, this is the second webinar in our series that we kicked off last Monday. We will have the recording of that webinar available online for those who've missed it. I'll find the link out for you guys to be able to send that through. And next Monday, we'll be back again speaking about the culmination of the project's work in the Connected Farm project. So today's webinar is on the use cases exploring digital technology in the pastoral system. And specifically, we'll have a few speakers today. You'll first hear from Kirsty Verhoek, who'll be talking about measuring heat stress in New Zealand dairy cows. I'll then hear from Paul Edwards and the proof of concept of using cow wearable data for pasture management. I'll then jump back in to discuss some of the work we've done around measuring cow experience and the potential of future technologies to do so. Just a reminder, we do have a Q&A function that should be on your screen. So if you have any questions at any point, feel free to pop them in there, and we'll do a bit of a Q&A session at the end of our speakers as well. So before I kick it off though, just want to give you a quick refresher about the project, the aims of the project, especially if you weren't able to attend last week when we went through it in a bit more detail. So the Animal-centric Dairy Industry Enabled by Digital Technology project was started in 2020 as part of a larger AgResearch-led NZ-BIDA New Zealand Bioeconomy in the Digital Age project. The Animal-centric project, though, was specifically an industry-focused project, which is a collaboration between AgResearch, DairyNZ, and Fonterra. And the focus of this is that animal well-being and digital technology coming together in response to increased customer and consumer focus on improving animal well-being and ensuring animals have a good life. And then looking at the potential of digital technology to measure, predict, and improve animal well-being. So our original aims were by the end of the project in 2024 to have easier access to metrics of animal well-being enabled by the integration of data and models and technologies to improve decision-making on farm and provide some of that transparency along the supply chain. And when we started, the original 10-year goal for 2030 of the project was that the New Zealand dairy industry is using quality of life proof points, and that's through seamless digital platforms for improved animal and system outcomes. So I will hand over now to our first speaker, which is Kirsty Verhoek, who'll be talking about measuring and understanding heat stress in New Zealand dairy cows. So Kirsty will just share her screen. Awesome, and take it away.
Oh, all right. Great, so everyone can see that cover slide and hear me okay? Excellent. I'll jump straight into it. Oh. So in the dairy sector, consumer and customer focus on well-being in our food production systems is intensifying, and this highlights the need for maintaining and demonstrating high standards of animal welfare to retain that market competitiveness and consumer trust. What we are seeing is increasing heat stress and weather variability, and these have negative impacts on our livestock. So these climate challenges affect the productivity and welfare of dairy cows, particularly those kept outdoors. Proactive measures are required to address these emerging welfare challenges, although being that it is great that we do have these animals outdoors in their natural environment. And this is where advances in data technology, data collection and technology integration play a key role, particularly providing those real-time insights into cow health and comfort, and understanding that impact of heat stress. And if you watched Jenny Jago last week, there was talk around increasing farmer uptake of technology, particularly cow wearables, that possibility to be able to collect animal wellbeing metrics, and that opportunity to really collect vast amounts of data. So this evolving landscape offers that opportunity for timely and informed decision making, particularly when looking at the impacts of mitigating the effects of heat stress. I'll just see if I can make that small. Just trying to move to the next slide. Here we go. And so when it comes to measuring heat load of a dairy cow, there is a lot around data and technology opportunities, and there's really categorized into two main ways. It's our resource-based measures and animal-based indicators of heat stress. So under resource-based measures, we're talking about weather variables, and this is where we have climate stations, mobile weather station data that are able to generate lots of data on the type of weather conditions our animals are experiencing. And this type of information feeds into indexes, which help us to assess the heat stress risk of animals. And you may have heard of the commonly used one, the temperature humidity index, or THI, and that combines air temperature and humidity. And it's commonly used, particularly overseas, where animals are housed indoors under controlled environments. But what that THI doesn't consider is outdoor factors. So particularly in our New Zealand context with our cows that graze outdoors, which has led to the development of what we call the Grazing Heat Load Index, or the GHLI. And this incorporates your air temperature, solar radiation, and wind speed. When we move on to more animal-based indicators of heat stress, the internationally accepted measure is respiration rate, as well as panting and drooling. And if you just see to the right there, we've got the checking breathing rate measure, which you can find on our DairyNZ website on how to measure respiration rate in cows. So this is quite a manual process where you go out and observe animals. And in the next slide, you'll see how difficult obtaining respiration rate is from our dairy cows. We then move into changes in behaviour, and we're getting more and more technology available where we can look at cow lying time. We can look at an animal's shade use. We can look at her time that she might spend near water, or changes in her patterns around rumination or reduced grazing. There's also other indicators such as body temperature, and we have loggers where we can do that, capture that information. Same for rumen temperature with boluses, as well as panting rate and wearing wearable collars. So this here, if you're very quick, is a video which shows our cows huddled up in heat stress, and you can see blink it and you miss it, trying to capture respiration rate. It's quite a difficult measure to capture, and this is really where it led us to go for our 2023 heat stress study under the NZ Bidder project, to look at other ways we can capture information on heat stress where we start to use technology. So the aim of this 2023 heat stress study was to update the existing grazing heat load index, which was initially based on a Waikato data set, and use a broader range of conditions across New Zealand. And on the right there, you can see the locations of the various enrolled farms from the study. We also wanted to investigate the use of sensor technology as an indicator of heat stress. And so are there other ways we can know if an animal is heat stressed other than, say, going beyond respiration rate? So this 2023 study collected data from 600 cows across 7 farms, and don't be alarmed that it says 8 farms on the right. We ended up dropping one of these farms from the data set. And from these 7 farms, we collected weather variables using weather stations, and we also collected animal heat stress indicators, and this included manual observations of cow respiration rate and drooling. So we collected over 22,000 manual observations, and we also collected information on rumen temperature using SmackTech boluses, and also panting rate using the AFI collars. And so just to give a bit of insight to the results from this trial, is what we found is that weather data shows that New Zealand cows experience various summer conditions. And so it just really shows you the challenge we have in capturing an animal's environment and how she might be perceiving it. It's not linear. You can see on the top left there is the range of temperatures that these animals are experiencing across these farms. The top right, the humidity, the bottom left, the solar radiation, and then the bottom right, the wind speed. You know, particularly you can see there farm 4 experiencing high wind speeds, which is a mitigating factor of heat stress. So it's the combination of these different weather variables that can impact how stressed that animal might become from heat stress. So what we also found is that the hotter it gets, the more heat stressed animals become. And you've got along the top here our North Island farms, so farms 1 to 4, and the bottom we have our South Island farms, farms 6 to 8. We have respiration rate along the y-axis, and then what we have done is we've grouped the temperature into bins. And you can really just see it shows how respiration rate is a good indicator of heat stress. So as the temperature goes up, the respiration rate also does. But again, this is not linear. You can also see that there was a lack of some higher temperatures for those North Island farms. I should add that summer 2023, we had a number of cyclones and it was a very wet summer. And opposite to this, in the South Island, we experienced some really hot days, and it was really nice for us to be able to show that cows in the South Island, particularly in Southland, Farm 8, do get heat stressed. So you'll recall that one of our objectives was to update the grazing heat load index, and we did this and we found that the updated version, well, you can see on the right there the existing 2022 version on the Waikato dataset and our updated version on the left. And again, you've got respiration rate going up y-axis, that yes, we were able to improve the predictability of this model, noting it is linear. However, there is still a lot of unexplained variation there. And so this is where starting to think going outside of linear modelling to understand how an animal becomes heat stressed is where our line of thought is heading. So that non-linear approach would really enhance our ability to predict heat stress in our cows. The second objective I talked about was, okay, well, what role do sensors have to play in understanding heat stress in our cows? And so the two I mentioned that we looked at was the rumen boluses for rumen temperature, where we use SmackTech, and this is on the left, and the other one is the AFI collars, which gave a panting time measure. So again, we have respiration rate on our y-axis, which, as we saw earlier, gives a good correlation with understanding an animal being heat stressed. And this is why we wanted to be able to compare that sensor data to respiration rate. So when you look at the rumen temperature 120 minutes after that respiration rate to take into account lag time, you can see that there is a relationship. As rumen temperature increases, so too does respiration rate. It's non-linear, with rumen temperature explaining around 32% of that total variation in respiration rate. On the right there, we have panting time, so our seconds per hour. Again, non-linear, but as our panting time is increasing, so is our respiration rate. And the panting time explained around 24% of that total variation in respiration rate. And that really is showing us some positive relationships there that we would like to explore further for future work around heat stress. So in summary, The utilisation of indices like the grazing heat load index really aid in evaluating those heat stress risks of outdoor animals. They're a useful tool for farmers going forward to help make strategic management decisions around the management of heat stress. So if we're able to forecast and predict a particular day and time when animals are most at risk, this will allow farmers to say, provide animals shade or turn on sprinklers so that they can reduce that heat load. What we're finding, however, is that the linear approaches like the grazing heat load index do present challenges in being able to characterise those animal conditions and comfort levels. And we did see in some of those earlier graphs that a lot of this is not linear. This is where technology really plays a key role. It allows us to start collecting animal wellbeing metrics such as rumen temperature or panting time, and start to understand how those metrics play a role in understanding an animal's heat stress. That sensor technology starts, well, if we go beyond that, starts to identify, okay, when are those thermal heat stress events occurring? What are the risks? And what are the potential mitigation strategies that might go beyond simply providing shade or shelter to an animal, so that we can really start to enhance that animal's well-being. Our next steps really are continuing our research into technology to help with that monitoring and mitigation strategies to really refine heat stress assessment in our pasture-based dairy systems across New Zealand. Thank you.
Thanks, Kirsty. That was awesome. It's great to hear all the work that you and the team have been up to in the past little while. Just a reminder, if you do have any questions for Kirsty or any of the speakers today, please do pop them into the Q&A function, and we'll love to address them afterwards. So our next speaker is Paul Edwards, who'll be talking about the proof of concept using wearable data for pasture management. Take it away, Paul.
Thank you. Can you hear me all right? Cool. So yeah, the rationale for this piece of work was that, as we've seen from that last webinar, that farmers are continuing to invest in wearable technologies, and we're approaching 1 million cows in New Zealand that are equipped with a range of different technologies. And this data at the moment is typically used for individual animal monitoring, in particular identifying things like heat detection or animal health events, things like that. And I guess the question that we and others had was, this represents a significant pool of data, and can that add value to improving our grazing management for our pastoral systems? And so we held a workshop with a group of farmers and sector sort of stakeholders and grazing management experts to really identify, okay, that's the topic, what is the specific research question we want to look at here, and came up with one around whether we can use animal sensor data as a non-subjective, near real-time indicator of feed availability. And so if we could do that, we would simplify decision making, and an element to this was trying to reduce cognitive burden for the farmer, because there's a lot of subjectivity and uncertainty in terms of estimating pasture mass, and so that really plays on farmers' minds. You know, are we making the right decision, or you're trying to factor in a lot of different things in order to make that decision. If it could work, save time, there's considerable effort goes into collecting quality pasture mass information. If we do it well, then we could be increasing our profit through better resource utilisation, as well as improving the value of the sensor technologies in terms of increasing. The more you increase the return on an investment, the more farmers that might be interested in making that investment, as well as linking back to the NZ bidder goals around being a proof point for animal feeding. So to investigate that question, we set up a controlled grazing experiment. There was 3 different, the animals involved in the study were offered 3 different pasture allocations, one at 100% of what we thought their requirements would be based on their level of production, energy requirements, pasture quality, etc. And then 2 contrasting treatments, one where they were only offered 80% of what their requirements were, and one where they were over allocated and offered 120% of their requirements. And that sort of plus or minus 20% was equivalent to about 200 to 400 kilos of dry matter per hectare in terms of that pasture cover, which is really within that range of kind of iometer, where you put a group of people in a paddock and say what's the pasture mass here. That's kind of starts to get into that range of subjectivity. In terms of how this played out, we did 24-hour grazings where they got a fresh pasture allocation after the morning milking. We ran the experiment during both spring and summer to reflect different stages of lactation, different pasture qualities, etc. And it was a pasture-only diet. So again, keeping that simple from a proof of concept perspective and really trying to understand what's going on here. And so if we move down to looking at that box there, within the experiment, there were 4 different herds, each of 25 cows. So there was 100 cows in total across the study. And each of those 4 herds went through 4 5-day periods. So period 1, where they were offered 100% of their estimated requirements. Period 2, where they were either offered their 80 or 120, back to 100%, and then switching to the opposite treatment that they had. So if they had 120, then they went to 80, or vice versa. And the 4 different herds, the sort of duplication you see there is one, to achieve that 80% or 120%, you can do that by changing the area. So essentially between the 100% and the 80 or 120, the actual pre-grazing pasture mass is the same. You're just offering them less or more area to achieve that allocation. Or the bottom 2 there is actually compared to the 100%, the area remains identical and they got a higher pasture cover for the 120% or lower pasture cover. And so that really, the goal of that was to put each of those herds through a range of different conditions that may be experienced on a farm, and really whether we could see that, whether we could see those differences appearing in the sensor data. And so just to kind of calibrate your eye with what that looked like, we've got that sort of 2x2 there where you've got adjusting the area or adjusting the cover and whether they were getting 80 and 120%. You can see some quite clear visual differences there where on the right-hand side of those photos is the pre-grazing, where the cows are, and the left-hand side is the post-grazing, where they were the day before. And you can see visually there's quite a clear difference there in terms of the 80 and 120%, where the 80%, they've grazed that down a lot lower than they have in the 120. In terms of what we measured, so we did a pre and a post grazing pasture mass, and then we also during daylight hours from when the cows entered after that morning milking, every 2 to 3 hours we also plated that area to generate a sort of pasture disappearance curve. It was done with a rising plate meter, but we took calibration cuts to try and improve the quality of the estimates being provided by the rising plate meter, and we also took pasture quality pasture samples to test for metabolizable energy, crude protein, things like that. And then those 100 cows across the experiment, they were each wearing 5 sensors simultaneously. So they had the AFI collar, the cow manager, the e-shepherd, ice cube, and they also had a SmackTech bolus in them as well. So just to start looking at some of the results. So I guess the fact that we had lots of different sensors on these animals, some of which were reporting similar behaviours. One of the questions that kept getting asked was, why are they saying the same thing? And I guess if we look at rumination time, the bottom right there, enclosed by the triangle, you can see that at a herd basis, this is based on the herd average, a minute of rumination time by the 3 devices that we were using that reported rumination time, they were basically saying the same thing. So they're, if you can see my mouse there, they're big blue dots, basically saying that there's quite a strong relationship between those things. If we look at our pasture metrics, we're sort of in this top the pre-grazing, some of the pasture quality metrics, and then the post-grazing. If we look down that column, you can see that the biggest dots relate to rumination time as the as a single individual predictor, where it was the most correlated with pasture mass. Whereas if you look at eating time there, you can see that essentially eating time was not a particularly good predictor of pasture mass or the quality. So that's looking at things at an individual basis. If we now pull it all together and say, well, okay, if you had one of those devices, so that's the columns of this figure here, if you used all of the data provided by that device, so for example, eating and rumination time, and we're wanting to predict or explain rather than predict, sorry, if we wanted to explain the variation in pre-grazing cover or post-grazing residual or disappearance, the difference between the two, at either a kilos of dry matter per cow or a kilos of dry matter per hectare basis. So those are important distinctions, I guess, because remember some of those groups were being offered different areas to achieve those different allocations, which would result in different pasture heights. And so we can see here in general that if we look compared to pre, post and disappearance, the highest values getting up towards 0.55, 0.6, the post-grazing residual was the best explained pasture metric. And that was in particular, you can see that the values for kiloliters of dry matter per hectare are also always higher. So, and whereas if we look at disappearance, generally, or as a proxy for kind of intake, that was not a metric that was particularly well explained by the data. We also looked at how we could improve that. So if we took the behaviours provided by those devices, but also then looked at duration in the paddock, because remember, these cows are entering and exiting the paddock to go to milking. If we factored in that as an extra piece of information that could be provided, that's the coloured dots are the base model. Then if we look at the including the duration of the paddock, this is the triangle, you can see that by and large that didn't really improve the predictions, other than perhaps the ice cube, which is a pedometer and so can measure steps. So of course, taking out some of the noise provided by walking to and from milking improved the amount of variation explained. And then if we added in pasture quality as another metric, again, by and large, didn't really improve the amount of variation that these models were explaining, with the exception of these two here, where they did improve things slightly, because these two were ones that did not improve did not provide rumination time as a metric. And so if we remember back to that previous figure, rumination time and pasture quality were correlated. So adding pasture quality for these two sensors was able to improve performance a bit. But yeah, overall, adding those extra levels of information typically didn't improve performance that much. We also had a look at, so that was just using the data available generated by these sort of devices in a standard kind of sense. The eShepherd, that did have an animal location every 10 minutes. And so we looked at creating some novel behaviours based on that animal location information. And so the two that we looked at, well, we looked at a number, but the two that came through as being most interesting were distance travelled, which interestingly is not necessarily that well correlated with steps, as well as the proximity to herd mates. So that's that metric that kind of looks at, are all the animals bunched together or are they kind of spread out? And so interestingly, those two novel behaviours had quite strong associations with pasture mass at a similar level to rumination time, if you remember back 2 slides ago to that triangular plot. So they were interesting metrics for predicting pasture mass, relating pasture mass. And interestingly, when you put those into the model, if we look at here, this is just an example one of post-grazing pasture mass at a kilos of dry matter per cow basis. If you just use the proprietary behaviours provided by the devices, adding in distance travelled and proximity to herd mates improved the amount of variation these models were explaining quite considerably, and which is quite interesting. If you flick back to the previous one, in general the per hectare metrics were actually better, but adding those location metrics brings these per cow ones up to a similar level to those per hectare ones. So just, I guess, sort of in summary, yeah, there is an increasing investment on animal sensors out there, and that does represent an opportunity to use that data for other purposes, for example, grazing management, and in doing so could save time, cost, reduce the cognitive burden, and ultimately lead to improved grazing management for farmers, as well as providing a proof point for feeding. And this piece of experimental work was as successful as a proof of concept, which I guess it needs to be clear that this is just a proof of concept at this point. And now we need to determine, or the next steps are to determine how it could be best used and actually what value it does have. So, for example, explaining 60% of the variation, is that good enough? Or is that really to provide value? Is that just sort of limited to general monitoring of post-grazing residual, for example, which could still be valuable in terms of giving an indication of whether a farmer's heading into surplus and needs to shut area out for silage, or whether they need to put some supplementary feed in, etc. The other challenge, I guess, is one, our experiment we were offering for what happens if you graze more than 2 paddocks. But the other interesting layer in there, of course, is if rumination time is the one explaining a lot of that variation. That's kind of something that doesn't necessarily relate to a paddock. The evening is when they spend a lot of time ruminating. So, how would you use it in different grazing systems, or if supplement is being added? Because, of course, again, if rumination time is the key driver, that supplement would be influencing the rumination time, and therefore potentially muddying the waters in terms of predicting different pasture masses. That's me.
Thanks, Paul. Thanks for an excellent explanation of your work there, especially as I'll be speaking a bit about some of the extra work we've added on top of your studies. So I will be speaking now about the potential uses of technology to measure cow experience and mental state. See, my slide's running. There we go. So first of all, how could we measure cow mental state or experience? And by mental state and experience, I'm kind of talking about the overall experience of an animal, positive or negative. You might call it affective state or emotional state in cows. And specifically, how can we measure positive cow mental states? So we're really good at usually picking up on negative experiences, but positive experiences are a little bit more tricky often. So if we look in the literature, there's lots of suggestions on what we could do to measure positive cow experiences. One of the most common ones you might come across is play behavior. This is potentially great for younger animals who tend to exhibit a lot more play behavior, but for larger, older animals, such as a dairy cow, that might be quite infrequent. So other options of what we could measure is vocalization, or grooming behavior, or potentially social behavior. If you take a look at those, some of these metrics, for example, were discussed earlier last webinar with the animal well-being metrics that Cheryl O'Connor presented. And that's a list of we went through 96 or something of them and focused them down to what we would measure in the domains of nutrition, environment, health, and behavior to get an overall understanding of cow well-being. Now, if you look at these ones that we've suggested here, play, vocalization, grooming, and social behavior, those are all in the behavior domain. And unfortunately, this is an area where there's not usually a lot of commercially available technology to measure it. So the aims of what we've done is we've looked at a couple of these metrics or measures to start to look at sort of pilot studies of how we could potentially use them for understanding cow experience. And the two we focused on here are vocalization behavior and grooming behavior in dairy cows. So first of all, I'm going to talk about cow vocalizations. And what do they mean? So cattle produce different types of vocalizations in different situations. They have a lower frequency nasal call in low stress situations, and then they have that high frequency loud, higher frequency call in higher stress situations. And previous research has found that the number and the intensity of these calls over time can change with the cow's affective or emotional state. So what we did in this pilot study was we attached microphones and just quite low-tech dictaphones that you can get from JB Hi-Fi, for example. And those are in a pouch, as you can see in this image of the cow attached on a collar just under her neck in this case, but what we've also done is attached it on the side of the neck. And we've developed an algorithm to be able to, first of all, identify a cow's vocalization from the sound that's going on farm. In a pastoral situation, it's quite noisy. There's other animals, tractors, wind, you name it. So first of all, isolating a vocalization from the background. Second of all, being able to identify the different type of vocalization that the cow emitted. So those low frequency and high frequency ones. And then third of all, being able to attribute the vocalization to a specific cow. So all the cows in this example were wearing microphones, and all of the microphones pick up the vocalization. So we were able to identify the loudest and attribute that one to the specific cow. So I'm really hoping that the next slide works. But what we did was we put these microphones on all of the cows in the study that Paul mentioned previously. So cows on an 80% allocation and the 120% allocation. And we looked at, hopefully the sound's coming through for you. No, darn.
It isn't. Look, I'm sorry, this is Jenna in the background. Yep. If you stop sharing and then start sharing again, there's a little button that says allow computer sound.
All right, I'll give that a go because it's quite obvious, quite an obvious difference. All right, share again.
You didn't see that come up, did you?
No, it didn't pop up.
All right, well, we'll just have to pass on this one. And
you'll have to trust me this time. But if you can see the image specifically of this cow here, yeah, they were quite vocal. Now this is us holding them back from their fresh break in the morning as soon as they've come back from morning milking. And then if you could hear the sound, it sounds like crickets, essentially. This is the 120% allocation. Again, the cows being held back from their fresh break in the morning, and you could hear a pin drop, essentially. So indeed, this is what our microphones picked up as well, is that the cows on the lower allocation vocalized a lot more than the cows on higher allocation. And then they had different spread of this temporally, like throughout the day, different times that they vocalized a lot more than each other. So it's important to note, though, that the lack of vocalization doesn't necessarily indicate a positive emotional state here. Potentially could be more an indicator of a neutral state compared to cows who are vocalizing to indicate that they're quite hungry and unhappy about a situation. So the next thing we looked at, again, another little pilot study attached to the grazing allocation study, was looking at scratching and grooming behavior. And we looked at quite another low-tech situation here. We placed stationary grooming brushes or scratching brushes in each of the paddocks and moved them every day with the fresh breaks that they got, or the fresh paddocks that they got. We then looked at all of the interactions with the grooming brush and the length and the duration of them as well. And if you can remember, Paul had the allocation changed by area and the allocation by cover. So an interesting result came out of this. We did hypothesize that the cows on 120% allocation who had potentially fuller bellies would spend more time or interact with the brush more. And this could be an indicator of a more positive, satiated state. And that's what we found in the allocation by cover. So these cows on the side here. The 120% allocated cows used the brush a lot more than the 80% allocated cows. But something interesting happened with the cows by area. So we saw essentially the inverse reaction here, where the cows on 80% used the brush a lot more and the cows on 120 used it a little bit less. We have some hypotheses for this. Potentially the by area, so the 80% had a much smaller area. So proximity to the brush is a lot closer versus the 120 that had a little bit more space. But definitely some more work in understanding and teasing out the relationship in terms of scratching and grooming behavior is important. And as I mentioned, this is quite low tech here. There's no technology, no wearables involved in this. So we did look at, again, a small little pilot study of using potential of using technology to be able to pick up this information automatically and be able to use it in future research projects. So what we did here was we used ear tags, and we tested out the ultra high frequency ear tags and regular low frequency NATE tags, essentially, and the antennas on brushes to be able to pick this up. So in the image on the right side here, with the circles, this is the ultra high frequency antenna setup, which is quite a lot more involved. And actually it does quite well at picking up interactions with the brush, but it has quite a lot of data that comes in, almost too much to handle with and cope with. And then if you can see on this one here, the small antenna is the regular low frequency NATE tag reader, which picked up interaction with the brush very well. So in summary, yeah, there's potential for existing technologies to be adapted and to be able to measure some of these tricky behaviors that could start to tell us a little bit more about cow experience and mental state. Definitely more research is needed in this area to be able to use this technology to tell something about the animal or the pasture. And definitely of the three use cases presented here today, this one is got the least tech available, and it's a little bit more complicated to understand. So yeah, a bit more on exploring and understanding animal needs and wants and how we can provide them, and the role of technology for this. And before I go into any questions, I'd just like to thank our speakers today, Kirsty and Paul, as well as everybody who's been involved over the course of this project over the years, from people who've attended webinars and workshops, our partner farms, and the rest of the project team from AgResearch, DairyNZ, and Fonterra. Yeah, thank you. And a reminder, if you do have any questions, do feel free to pop them in the Q&A section. Love to start to answer them. We got some published, that's great. I might kick it off. Oh, this is a good question for Kirsty. Oh, maybe I'll stop sharing my screen so that Kirsty can pop up there. Kirsty, it's good to see that technology appears to be able to predict heat stress in cattle. Are you looking at ways to mitigate heat stress and monitor if improvement is seen? Many farms have limited ways to mitigate heat stress, e.g. lack of shade trees or shelter belts, especially in places such as the Hauraki Plains.
Yeah, that is a really great question. We're really keen that our next round of research that we're looking to embark on looks at mitigations that go beyond just providing shade. We know that animals are variable in their heat stress susceptibility, and this has been the great thing about the technology that we have at our hands and the wearables is that we're getting a better understanding of how our animals are responding to heat stress, how different they are in their response. And so that is then informing us to be more strategic in how we utilize our mitigations. So for an example might be, why provide shade to the entire herd when only 20% of the herd might need that shade? So yes, that is our next round of research, is to start looking at, okay, what are our opportunities around mitigation and how can we be more strategic with it? The tricky part around that monitoring, if the heat stress has been improved, is that it's hard to have a control animal. They're all exposed to the same temperature at the same day. So it's then starting to get be able to use that technology in a way that we can maybe have a baseline and understand how the animals are deviating from that baseline to see if a heat stress mitigation has had an effect. So yes, this is part of the focus for our future research.
Awesome, thanks, Kirsty. Yeah, if you have any more questions, please do pop them through. I just have potentially a question for Paul. Yeah, your results there were quite promising. Do you have any insights on what needs to happen to take this from a proof of concept and actually make it useful for farmers?
I mean, essentially a lot more data collection and testing. As I said, it's a proof of concept that I think demonstrates that yes, there's potential there to use that data set, provided by these sensors to be able to improve grazing management. But there's a lot more range of environments it needs to be tested in, as well as just how you would actually use it to provide value, if that kind of makes sense. So it's clearly never going to be, well, maybe never is too strong a word, but at the moment it's a long way away from being able to say, right, the cows are in this paddock and based on this data that it was exactly this, right? Like there's a lot of noise that's, I think, most likely always going to be there, but that doesn't mean that that's not valuable. So it's how do you use it to improve your decision making that needs to really be thought through, and I think ultimately probably that comes down to commercial companies seeing the potential in it and the value, and then really driving that, because if that's not there, then that's the route to how a farmer would use it. If that sort of interest isn't there from them, then that makes it an awful lot more challenging.
Thanks, Paul. That's great. Yeah, I've had another question come through, possibly for me there. What do you envisage the outcome from your research looking like in terms of farmers being able to use this data? Yeah, so I think we're probably a little bit early days in the use of the microphones and the brush use sort of data at this stage. It's especially as we don't really have anything commercially available to automate that measure. Again, you can do this. You can start to take a look at that behavior manually, and I think a lot of farmers already do that. It's especially in terms of the vocalizations, they're listening, and it's quite obvious. But yeah, just a case of continued research into that and continued work in the technology space to get that into a more automated system for sure. Yeah. Do we have any more questions come through? No? Perfect. We have come to the end of our time. So I might cut it off there, but if you do have any questions, do feel free to reach out to any of our speakers today or from last week as well. And just a reminder as well that we have our next webinar series next Monday, same time at 12 o'clock on the development of the connected farms. So we really hope that you'll come back and join us for that one. Yeah, and at that, thank you so much for attending and hope to see you next time.